When light encounters a boundary between two media, it can either be reflected or transmitted. The law of reflection of light states that the angle of incidence equals the angle of reflection, or theta I equals theta r. Imagine an object with height h, placed an object distance p in front of a plane mirror. The rays for our ray trace will all begin at the tip of the object and must obey the law of reflection. The first ray we trace is sent horizontally, perpendicular to the mirror, and retraces its own path. The second ray could be sent to strike the mirror at half the object height and will be reflected back to the base of the object. A third ray could strike the mirror at 0 height and will be reflected downward at the same angle. The reflected rays all appear to diverge from one point behind the mirror. Tracing them back locates the image in the mirror at an image distance q. Note that for a plane mirror, the image distance equals the object distance, and the height of the image equals the height of the object. In this experiment, we place a plane mirror along the center line of a sheet of paper and place a dot to represent the tip of the object off-axis. A laser leveler is used to generate a ray passing through the tip of the object in some direction. Use a pencil to trace both the incident and reflected rays. Send other rays through the dot at other angles and trace those rays too. One can see that the rays diverge from a point behind the mirror. Trace the reflected rays back behind the mirror to locate the image point. Measure to see if P equals Q. The index of refraction, n, is defined as the ratio of the speed of light in vacuum to the speed of light inside some medium. N is always greater than or equal to 1 since, according to the special theory of relativity, the speed of light in a vacuum, c, is the fastest speed in the universe. N is larger in a medium with a slower speed of light. A light ray passing from a medium with small index of refraction n, that is one where the speed of light is relatively high, into a medium with larger index of refraction, n2, where the speed of light is relatively low, is bent toward the normal. Snell's law states that the product of n1 times the sine of theta 1 is equal to the product of n2 times the sine of theta 2. The angles are measured with respect to the normal to the surface of the interface. Use a protractor to measure off some angles relative to the vertical axis and sketch lines. Place the container filled with water with a flat interface along the horizontal axis. Shine the laser beam along each of the sketched lines and trace the emergent beam when it exits the water. Both the incident and refracted angles are shown. Trace emergent rays for each of the incident angles and measure the incident and refracted angles relative to the vertical axis. Since the light is incident from air into water, n1 is very nearly 1, and n2 is the index of refraction of water. By Snell's law, the sine of theta 1 is linearly related to the sine of theta 2, with the slope of the straight line being n, the index of refraction of water. Here is our plot of sine theta 1 versus sine theta 2. The slope may be compared with 1.33, the index of refraction of water. When you look at an object located beneath the water, the rays of light from the object are bent away from the normal, and the image appears at a shallower depth called the apparent depth. If you're hunting fish from above the surface using a spear, you'll need to aim deeper than where the fish appears. On the other hand, if you're shooting a fish with a laser beam, you'll need to aim directly at the image, since the laser beam will be bent downward at the surface as well. If you're looking nearly straight down into the water, that is, at small emergent angles, the ratio of the actual depth to the apparent depth is equal to the index of refraction of the water, approximately 1.33. For example, if you wish to wade in a pool that appears to be 1 meter deep, you should plan on the actual depth being 1.33 meters. We can see this ratio by examining the ray coming from an actual depth of P and giving an apparent depth of Q, and considering the angles θ1 and θ2. According to Snell's law, n times sine θ1 equals 1 times sine θ2. For small angles, the sine of θ1 is approximately the lateral distance x divided by p, and the sine of θ2 is approximately x divided by q. Thus, n is approximately p divided by q. Trace around a square of glass and send a beam from the laser at a low angle of incidence and passing through the point in the middle of the base. Trace the short stub of beam that emerges after passing through the glass. Ignore the portion of the beam that passes over the glass entirely. Perform a similar ray trace with the beam entering from the other side, again at a low angle of incidence. The two beams are seen to diverge from a common point along the vertical axis. For good measure, trace a couple more rays. The actual depth p is the depth of the glass. The apparent depth is the distance of the virtual image to the surface of the glass. The ratio of p to q should be approximately n, the index of refraction of the glass. We now turn to the concept of total internal reflection. When a beam of light emerges from glass or water into air, it is bent away from the normal. As the incident angle is increased, the refracted angle gets even larger, approaching 90 degrees. At the critical angle, the ray is refracted to exactly a 90-degree angle. Any angle of incidence greater than the critical angle leads to a totally internally reflected ray. The critical angle is related to the index of refraction of the material. Again, applying Snell's law, we find that n sine theta c is equal to 1 times the sine of 90 degrees. Solving for n gives the index of refraction as the reciprocal of the sine of the critical angle. Send a laser beam through the glass such that it enters normally but exits the upper surface and is bent away from the normal. Increase the angle of incidence until the emerging beam is aligned with the surface. Find the minimum incident angle where the beam encounters the surface and is totally internally reflected rather than refracted. This is the critical angle. You can calculate the index of refraction of the glass from this angle.